Let's do a problem similar to the previous one. So I'm again going to have this ketone carbonyl. But let me modify the starting structure slightly. Let me put a substituent group here. So this is just going to be an OCH3 group. This is called an ether, by the way. When you have a carbon, oxygen, carbon, that would be an example of an ether. So you've got an ether functional group here. You have a ketone functional group there. And then we're going to do the same thing that we did the last time. So in step 1, we're going to add hydride. And in step 2, we're going to add H+. And so I'm just going to ask you a series of questions here, and then we'll work through them. But I want you to be able to see if you can work it through on your own. What I want you to draw, given your experience from the previous problem, are the possible products of hydride addition. Maybe there's more than one possible product. And then I want you to tell me what is the stereochemical relationship between or among, depending on how many products you come up with. I don't want to tip my hand too much. What is the stereochemical relationship between or among the various products that you're able to generate from this reaction? The principle is the same as we had the last time. This carbonyl group is flat. In other words, it sits in one plane. And really, I guess I should include the carbons that are attached to the carbonyl group, like that. There we go, okay? So this whole carbonyl unit is flat, and the hydride can either add from the top, or it can add from the back. So if you were nonplussed by this problem originally, give it a try now. What's the product of hydride addition from the front? And then separately, what's the product of hydride addition from the back? One key to this problem is that all of the chemistry that we're describing is happening at this carbon, this carbonyl carbon. I'll put a little star there, all right? Remember, this is not a stereogenic center at this point, but maybe it's one of these prochiral centers. Nothing happens to this center here, all right? So you might have noticed there's already a chiral center in the molecule right there. That is completely unperturbed by the reaction that's taking place at the carbonyl group. So there it is. And then first I was going to draw the product of addition of hydride from the front. So there it is. There's the hydride. And that's going to give you the OH group in the back. So this was top face addition. And then the other possibility is if hydride had come from the other side, from behind the board. Again, nothing has happened over here, so I just have to redraw this chiral center with nothing changed. And then over here, the hydride came from the back, and the OH group is forward. So this is the product of bottom face hydride addition. Have we generated a stereocenter at the starred carbon? So here it is. Yes, I have. So this was a prochiral carbon. We added hydride to it. We got another stereocenter. So the final part of this question was, what is the stereochemical relationship between these two structures? Well, they have two stereocenters, 1 and 2, 1 and 2. They have the same configuration at this one, but a different configuration at that one. So what do you suppose they are? Well, they are diastereomers. The difference between this problem and the previous problem was that in the previous problem, we just had a CH2 group here. We didn't have a second chiral center in the molecule. Whereas in this case, we do. We have a second chiral center that doesn't change. So relative to this stereogenic center, there are two different possibilities, OH back and hydrogen forward, or hydrogen forward and OH back, whereas this center stays constant. So you have the possibility for diastereomeric products instead of the enantiomeric products that we saw in the last example.